morning.
Morning.
First exam out of the way, right? Looks like I'll be starting exam grading this week, and this class happens to be the first one on the docket. Once I get started, it doesn't take me long, a couple of days. You'll know when exams are graded because they'll be posted onto campus. And also, as a general rule, if you ask me when they're going to be graded, it takes me longer. Before the exam, we look at cofactor expansion. It's a good method, but it is flawed. We're going to look at, in my opinion, a better method. So we're going to examine the effects row operations have on a determinant. Consider n by n matrix A and an n by n elementary matrix E. Right, so remember, elementary matrix, you have three types, right? One for each of the row operations. So type 1 represents swapping rows, type 2 multiplying a row by a non-zero constant, and type 3 adding to a row a multiple of another row. Determinant of E times A is the determinant of E times the determinant of A, where the determinant of E is one of three. -1 if E is type 1. The non-zero constant K if E is type 2. And 1 if E is type 3. So we can summarize this. Interchanging two rows of a matrix changes the sign of the determinant. So if you swap two rows in a matrix, the determinant gets multiplied by -1. If you multiply a single row of a matrix by a non-zero constant, then you just multiply the determinant by that same constant. Finally, adding to a row a multiple of another row has no effect on the determinant. So swapping two rows, determinant gets multiplied by -1. Multiplying a row by a non-zero constant, the determinant gets multiplied by that same constant. And then doing your type 3 has no effect.
So is that why with QR factorization you can do interchanging rows or multiplying by scalars?
QR? Does QR use determinants?
I don't think so.
More likely the reason that you're talking about QR or LU.
QR.
More likely than not, that restriction comes from the fact that the QR method actually uses Gram-Schmidt normalization. That's probably why.
To go over again for the second one, it's multiplying the entire determinant by that scalar?
Yes.
Okay.
Right, so you get a new matrix simply by multiplying a row by a scalar. then that new matrix determinant is the old matrix times the scalar. The determinant of the old matrix times that scalar. That's what happens. The point of doing this is to try and get the matrix you're finding the determinant of into triangular form. Either upper or lower does not matter. Upper is the easiest one to get to. Because then we can use this property. If you take the determinant of a triangular matrix, it's just the product of the diagonal elements. And that is our process. We use row operations to get the matrix into triangular form. You don't need to worry about it being in echelon form, reduced echelon form. You need the leading elements to be 1. You can if you want to. It doesn't change anything. Keeping track of your row operations and what you're going to have to multiply by. Once you get to triangular form, just multiply the elements of the diagonal. This was mentioned, now we're formally stating it. Let A be an n by n matrix. If A has a row or column consisting entirely of zeros, the determinant of A is 0. As a corollary to that, if A has 2 identical rows or columns, its determinant is 0. And again, this was also mentioned. We're now formally stating it. N by n matrix A is singular if and only if the determinant of A is 0. If and only ifs are nice statements, because it means both the ways you read it are true. So if you find the determinant of that matrix is 0, you know it's singular. And if you know the matrix is singular, you know its determinant is 0. Again, just formally stating it now. I think we verified this Tuesday. You have two n by n matrices, A and B. Determinant of their product is the product of their determinants. So we're going to go ahead and calculate determinants by using their operations. Again, we'll start with a 3 by 3 because that is easy enough to verify that our algorithm is correct. If we go back real quick, actually, to here, I wanted to say, if in the process of getting it into triangular form, you get two identical rows or a row of zeros, you can just stop and go, the determinant has to be 0 by this. Right, so start with your determinant, your matrix. We want to get this into diagonal form. So let's zero out the elements below that 2. That's going to require a fraction. So why not make that? You don't have to.
But doesn't that change the determinant?
We'll take that into account. So I'm multiplying a row by a constant. Which means this new determinant is the constant times the old determinant. Specifically 1/2 in this case. Let's call it a sub 1. Right, that's what number 2 says. So multiply your new determinant by its reciprocal. Right, multiply by 1/2. Our new determinant is going to be multiplied by 2. Bless you. Thank you.
Wouldn't it just be easier to wait and calculate all the multiples and then do the determinant A? Would that also work?
What do you mean calculate all the multiples? So just keep track of it separately and then multiply them at the end?
So just keep it on that one side. Just keep all of the multiples on one side and then do the determinant A.
I'm not quite following. Keep all the multiples on one side. What do you mean?
So 1/2 R1, right? So row 2, then you would put the 3 next to the 1/2, and then
Right.
keep going, and then find the determinant A, and then use all of them.
Which I think yeah, so you kind of just keep them off to the side somewhere. Again, triangular form and then account form, right? You could do that, which is what I'm doing here. But you have to remember, we're not going to calculate determinant of A at the end. We're calculating determinant of that new triangular matrix, not of A. Which is typically why I do it this way. I just kind of try to keep track of everything as I'm going along so I don't forget. But yeah, if you want to keep that off to the side somewhere and worry about it at the end, that's fine. This makes zeroing out those two terms easier now. It's going to be what? -5, row 1 plus row 2. -8, row 1 plus row 3. And with this type of operation, your determinant doesn't change. Which means we don't have to worry about multiplying our new determinant by anything. Oh boy. -15/2 plus 6.
-3/2?
It's -10 plus 7, -3.
Right. No, -3, sorry.
Should be -3, right? Yeah. I was looking at the wrong line, so I confused myself. And -16 and 1, -15. Getting rid of that -3 is fairly simple, even with the fraction. So I won't actually worry about making that -3/2 a 1. It'll just be, what, -2, row 2 plus row 3?
Yeah.
Again, it's a type 3, so the determinant doesn't change. And we get 6 minus 15. Triangular form. Two times -3/2 is just -3. -3 times -9 is 27. There's your determinant.
No. That equals 27 halves. Oh, right, that's the 2. Forget that.
Verify that by using the definition of the determinant on that 3 by 3. And you should get 27. And that's why we use the 3 by 3 to start, so we can verify it. Well, let's do it. Keep track. 2 times 6 times 1, that's 12. 3 times 7, oh my god. Okay, no, I don't feel like doing that in my head. I'll let you do it then. That's going to get pretty large and hideous. Oh, this was tough. expansion, maybe. Or one similar to it anyway. If we're doing cofactor expansion, we have a nice column and a nice row to work with. But we don't need to worry about that. We can just look and go, oh, it's not triangular. Just multiply diagonal elements.
What happens if it's lower triangular?
Doesn't matter, same thing. You just multiply the elements along the diagonal.
So how is lower harder than upper?
It's not, it's just we're used to getting it into upper triangular using the row operations instead of upper. Right? But the process is the same, you just kind of go in reverse, right? So if I wanted to do upper triangular, here I'd start with this one down here, zero out everything above it, and then move on to whatever happens to be in that position afterwards, zero above it.
Well, that also looks like not bad.
No,
One.
yeah, so that's what I said. It's just we're used to doing it the other way, which is why we typically stick with that.
Okay.
But you don't have to. That's going to be, what's -6 times 20, which is -120. Is that determinant? So now let's actually try it that way for this one. Make it lower triangular instead of upper. Negative row 3 plus row 2. The third, row 3 plus row 1. So that would be us. That would be 0. Negative 1 3/4 is -1/4. 4 plus a half, 9/2. That's where it's going to go. A third plus a half. 5/6. Negative 4/3 minus 1, negative 7/3. Oh, that's not cool.
Turn row 2 into 2/9.
Yeah, I'm just going to multiply row 2 by 2/9 to make that a 1. Which means we'll multiply the resulting determinant by 9/2. That would be what, negative 1/18 there? 7/3 row 2 plus row 1. And now what does that become? -1/18 times 7/3 plus 5/6. What the heck is that? Picked an awful one to decide to do lower triangle for.
Would that be 41/18? Oh wait, no, never mind.
I got 19/27. At least that's nice, where we got 2 1s. And so what is 9/2 times 19/27? That's going to be what?
19/6.
A half times 19/3. Which is 19/6. Which is what you get if you make it upper triangular instead. That's how I did it in my notes.
Was that easier?
Yes, a lot easier. So I said I picked the wrong one. Well, let me rephrase that. It doesn't have as many fractions like this. It also took me 2 steps instead of the 3. But I could have done this in 2 steps without making that long. So fractions weren't as bad.
So where does the whole type 1, type 2, type 3 come in?
The type of row operations.
Oh.
Type 1 is swapping 2 rows, type 2
Yeah.
is multiplying a row, and then type 3 is the multiple of a row plus another row. Here's the question. Do I want to swap rows or deal with fractions? I dealt with fractions in my notes. The fractions aren't terrible, actually. I'm not going to swap rows. because this is the ideal situation. Where if you only use type 3, you don't have to worry about multiplying by anything. Because type 3 doesn't change the determinant. So I'll show that off. Because I am going to be swapping rows in the next one. Row 1 plus row 2. Negative a half row 1 plus row 3, and then a half row 1 plus row 4. That should zero out that first column, right? Five minus 3, negative 3 plus 2, negative 2 minus 5, so that's the second row. Negative 5 halves plus 3.
1 half.
3 halves minus 2.
Negative 1.
And it's 1 plus 2. Five halves minus 6.
7 halves? Or negative 7?
Negative 7 halves. Negative 3 halves plus 4.
5.
And then negative 1 plus 3. It was a type 3 operation, so no changes. Well, now we can easily zero out everything in the second column. What are we going to have to multiply 2 by to get negative a half?
Yeah, negative 1.
Negative 1/4. What about to get positive 7 halves?
7 4.
Again, since we're only using type 3, the determinant doesn't change. A quarter minus a half.
A quarter minus a half. Right? Negative.
Negative a quarter, right? Seven quarters plus 3. Now we have to multiply 7 fourths. Negative 7 fourths plus 5 halves.
Three halves?
3 halves.
Negative 3. Wait, hold on. 3/4, sorry.
3/4. Negative 49/4 plus 2.
Negative 41.
What are we multiplying -1/4 by to get -3/4?
3.
Again, type 3, so no change in the determinant. Three times 19/4 minus 41/4.
10/4. Or no, 19.
16/4.
Which is
4.
Now we have triangular. Oh, that product is nice. 2 times 2 is 4, times -1/4 is -1, times 4 is -4. There's your determinant.
Wouldn't it just been easier to swap the rows, because it would just change the sign, so it's like not that big of a deal?
I'm just showing the ideal situation where you don't have to worry about any of that. Because I'm going to swap rows in the next one. So I'm going to at least show one where I do nothing but type 3. Again, no matter how you do it, it doesn't really matter. Right? It's just subtractive what you're doing. Five by 5. So to be honest, none of the previous ones would have been terrible with cofactor expansion, necessarily, right? This one probably would have been, if we use cofactor expansion here. Because the best we're going to be able to do is get a single 0. Right, so we get 4 4x4s instead of 5 4x4s. What do you do? At best. This is going to be made a lot easier using row operations. Here, I am going to switch 2 rows to start.
Does the whole, like, multiplying in a diagonal, the whole thing, does that work or no?
What do you
Like,
mean?
when you get bigger than 3, does it
Oh,
just
the
not
way
work?
that we did 3 by 3?
Yeah.
No. It only works for 2 by 2 and 3 by 3. Anything above that, you cannot use that method. Yeah, it sucks. So you have to do one of 3 things for 4 by 4 and larger. Calculate all of the permutations, right, because you're going to use the definition. Well, 4 by 4 has 24 permutations. 5 by 5 is 120. So good luck with that. Have fun. Do cofactor expansion, which 4 by 4, not terrible. 5 by 5 starts to get a little bad. Or row operations. I guess you could throw it into a calculator, but I'm testing on using these methods. And once you get to 6 by 6, forget it. 6 by 6 has 720 permutations. So you have 720 terms using the definition of the determinant. So what we notice row 1, 2, 3, and 4, all of those entries in that first column are positive. And it's negative in the fifth, so I'm going to flip row 1 and 5. So remember, this is the result if you flip 2 rows. This way. Right, E times A I'm going to say is A1. So determinant of A1 is negative determinant of A. But we're looking for determinant of A. Because it's just a negative 1, you just multiply your new determinant by minus 1. Right, so what you have to keep in mind is the summarization, these 2 slides, give you the determinant of your new matrix A sub 1, right, after you perform the row operation, which is not what we're looking for. We're looking for the determinant of A. Again, type 1, just multiply by minus. You can't really misinterpret that. Type 2, though, you have to be careful. That's where you multiply by the reciprocal. And then type 3 has no effect. So we're going to multiply by a negative. And then our new determinant. We want 2 row 1 plus row 2, row 1 plus row 3, 3 row 1 plus row 4, and then 6 row 1 plus row 5. Finish off row 2. Negative 2 plus 1. Then negative 6 plus 1. Eight minus 2. 4 plus 1. Finish off row 3, be negative 1 plus 1. Negative 3 plus 2. Four minus 2. 2 plus 3.
We can't see that.
I know. I'm keeping that up there so that I can, so I don't have to keep flipping back and forth. And then once I finish it off, I will switch back. What was next? It was 3 row 1. So negative 3 plus 0. Negative 9 plus 2. Who's times 3, right? 12 plus 3. And 6 minus 1. Last one. Negative 6 and 2. Negative 18 and 1. 24 and 0. 12 and 5. What you should get? Oh, that's nice. Let me do my negative. Negative 3, row 2 plus row 4, and then negative 4, row 2 plus row 5. Right, because row 3 already has that 0. What should we get for row 3? No, not a trick.
That's the same.
Same thing, right? Just not doing anything to row 3. That's nice. What does row 4 become now?
Messed up, right?
Hmm?
Messed up, right?
What do you mean messed up? It's going to change if that's what you
Yeah.
mean.
But, like, isn't there going to be a problem with it?
Why?
I don't know. Just guess.
So what do we get for row 4?
Negative 3.
What do we get for row 5?
Right.
It's going to be what? 8 and 3, right? Multiplying by. All right, so finish out row 4.
Routine.
Finish out row 5.
Six.
So now at this point, there's a few ways to proceed. Could multiply row 2 by 13. You could flip row 4 and row 5, and then multiply your new row 4 by 6. Or you can go, I'm almost there at the finish line. What am I multiplying 13 by to get negative 6? What is it?
-6/13.
That's what I did. I'm already there at the finish line. There's not a lot of fractions to deal with. But again, remember, there is no wrong answer on how to proceed from here. You could do anything that I just mentioned. As long as you keep track. What is that last entry going to be? So negative 6 times 30, negative 180. What is 12 times 13?
156.
Negative 180 plus 156 all over 13 would be the answer, which is negative 24.
I get the extra one in my calculator.
That'll do it. You know, what did I say when we started our operations? Arithmetic is hard. All this stuff is easy. We can do this. Just the arithmetic itself is difficult. And just wait till you get to like advanced physics, and you get all the physics right, and you do something like 3 plus 5 is 9. And screw up the entire answer. So we have the negative. We now have triangular, right? Okay, so how many negatives do we have? 1, 2, 3, 4, 5. So the answer is going to be negative. Bunch of ones, we can ignore those. Yep, and look at that. 13 times 24 over 13. Negative 24, and you're done. So that's negative 24. Certainly a lot easier than using the definition and doing 120 terms. I'll leave you to decide if you'd rather do cofactor expansion or not. You're going to say something? You were going to say something?
No.
Thought I saw your hand up.
What is?
Thought it was. Hallucinating. Also keep in mind, you can combine the methods. So let's say you get down to here and you decide you just want to do cofactor expansion. Go ahead. Or you do cofactor expansion to start and then you decide to do row operations on your resulting matrix. Right, let's say we got like a column that had all but 1 zeros. Do cofactor expansion along that column. Now it's a single 4x4 determinant. Now use row operations to find that determinant. So you can mix and match your techniques as well. Let's take a look. So use what we know about the row operations, the determinant of triangular, and these two. What happens if you get a matrix where one row or column is a multiple of another row or column?
It's zero.
Determinant will automatically be 0. Right? Because you just do a simple type 3 row operation to get that multiple row to 0 out. Then you're left with case 1.
What if there's 2 columns? It would be
It'd be the same thing if it was columns instead of rows.
So then you would do the
You would technically do a column operation, which we didn't study, but it's equivalent because everything we just discussed is also the same for column operations. So that reasoning would be the same. Let's call it a corollary to this. So again, let's say you're doing some operations and you get to a point where you notice that one row is a multiple of another row. You're done, determinant 0. Likewise for columns. If you find that you have a column that's a multiple of another column, you're done, determinant 0. Questions on this technique? Let's do polling by show of hands. Who prefers cofactor expansion? Damn, not a single person? Thought I'd get at least one. You're kind of on the fence. Depends on the situation, right? That's the right answer. Depends on the situation, on which one's easier. You were given a 10 by 10 matrix. What would you default to?
What if there's a row of just one and then the rest is
You're still going to wind up having to do, if you do cofactor expansion, you're left with 9 by 9.
oh, yeah.
At which point, yeah, then I'm probably looking at it and go, maybe row operations will be nice. Right, so that's what I mean, kind of want to mix your techniques. If you notice, oh look, I have a column of all of zeros except for 1, 1. Cofactor expansion. Reduce the size of the determinant. And then go from there. Who knows, maybe you get lucky, and when you do that, you find the determinant you're left with has a row that's a multiple of another row, and then you go, I'm done. Determinant 0. I'm happy. So the second project, which again is very easy, it's just basically copy and paste in Mathematica. I don't think there's really anything different. I think it may ask you to interpret a result, but there's really no calculations you have to do on your own without guidance. So that will be due Thursday. And then the MyLab homework on this stuff is due next Tuesday. Oh my God, we're already at the end of February. Spring break is 2 weeks away. So you were a sophomore? Sophomore?
I think.
I still got 2 years.
It's hard to say because my credits.
Unless you go to grad school. On Thursday, we look at 2 applications of the determinant. Finding inverses using determinants, which is awful, and Kramer's rule. Kramer's rule is useful, especially in differential equations. Then next week we start linear spaces, so we get into the very abstract starting next week. So prepare yourselves.